Thank you, Joanne. Hi, everybody. It's great that you could join the lecture. And today I'm going to talk to you about space weather, and in particular about solar particle radiation. And this is the topic that I do research on here at the university. And so what I want to do in this lecture, first of all, is tell you a little bit about the sun and give you some background about solar physics. And then I will talk about what solar particle radiation is, and I will tell you a bit more about the effects on the Earth. So in this image here, you can see the sun on the left, and you can see that the sun is producing energetic particles that may reach the region near the Earth, which is up here. So I will talk about the effects of this particle radiation, and I will also say a little bit about my own research and what we do to study the particle radiation. So let's start to say something about the sun. When we talk about the sun, most people start thinking about a warm, sunny presence, something that makes our holidays nice. And also sometimes we think of the sun as a really good source of energy. We know that with solar panels, we can harness the sun's energy and produce electricity. But what this talk is going to be about is something different. This talk is going to be about the solar activity and how solar eruption can influence the Earth and the area of space near the Earth. So when we talk about solar activity, the first thing we need to talk about are sunspots. What you can see here is a drawing that was made in 1613 by Galileo, who looked through his telescope and noticed that when you look at the disk of the sun, the disk is not uniform. You know, we always draw it as a uniform yellow thing, but in reality, it's got these spots that you can see in his drawings here. So immediately, he understood that these spots are important, and it turns out that they are very, very important for the activity of the sun. And probably at this moment, it's a good time to say that whenever you're looking at the sun, either with the naked, well, you should not look at the sun, sorry, either with the naked eye or with a telescope, because it can be very dangerous for your eyesight. So whenever we look at the sun through a telescope, we have to use a special filter. It's a solar filter that makes sure that our eyes don't get injured. So never look at the sun directly. Now, these days, we look at sunspots using much better telescopes than the one that Galileo had. And so we can zoom in into a sunspot and obtain a movie like this one. So this is a movie of a sunspot at very high resolution. And what you can see is that the center of the sunspot is dark compared to the region around it. So the reason why the center of the sunspot is dark is because it is cool. It is much cooler than the area around it. And these days we understand that the reason why the sunspot is cool is because of the strong magnetic field that goes through the sunspot. And I will talk a bit more about that. So the previous movie was looking at the visible surface of the sun, but we're also very interested in looking at the outer part of the outer layers of the sun, and you can see them here in this solar eclipse image. So as you probably know, when there is a solar eclipse, if it's a total eclipse, such as in this picture, the disk of the moon completely shields the disk of the sun. It covers it completely. And so when it does that, it reveals the structure of the atmosphere that you can see with all these beautiful rays and also these structures here that we call cusps. So this is the atmosphere of the sun. It's called the corona, nothing to do with the coronavirus. And essentially, we are very interested in terms of solar eruptions and solar activity in this layer of the sun. So these days, what we have is, we have a lot of spacecraft missions that are monitoring the sun all the time. And then the spacecraft can produce movies such as this one. So this on this side is a movie of the whole sun. And what you can see is, you can see images taken using a special filter that only collects EUV light. So it's an EUV image of the sun. And with this type of filter, what we can see is we can see these regions that are bright, like this one here, this one here. And in this smaller part, you see a zoom in of this region here. And so you can see these loops, and they are not static. They are moving all the time, and you can see brightenings, like flashings of light. So these are called solar flares, and the region where these kind of things happen is called an active region. So as the name says, an active region is a place where things are happening on the sun. And it turns out that an active region is basically a place where sunspots are located. So when we look at the particular region using the EUV, we have this movie up here. When we look at the region in a different range of wavelengths, the visible range, then we see the sunspots. So it's a bit like the sunspots are located under all these loops that you can see here. And interestingly, the reason why we have these very pronounced loop-like structures is because the sun has a very strong magnetic field. And so the gas of the sun is confined in these loops, and the magnetic field is sort of holding the shape of the gas. So here is another movie, this time using various different filters of the sun, so 3 different filters. And what you have here is a solar active region, which is bright in all the images. And as you look at the movie, you can see that actually some mass is expelled from that region. So that's what we call a solar eruption. It's going to happen again in a minute from this region here. And essentially, this is a very important phenomenon in space weather, because it is what starts the whole chain of processes that produce solar eruptions. So now we talked about sunspots, and we said that sunspots are very important regions for solar activity. And what you can see in this plot here is you can see the number of sunspots plotted versus time. Okay, so what we can see, and this is a plot that starts in the 1950s and ends at the present time, you can see that the number of sunspots on the sun increases over time, and then decreases, and then increases, and then decreases. So there is this regular pattern, which is called the solar cycle. And over an 11-year period, the activity of the sun goes from low number of sunspots to high number of sunspots, and then low again, and so on. And this is very important because at the time when there are very few sunspots at the sun, solar activity is low, and at the time when there are many, there are a lot of solar eruptions and a lot of space weather. So what you can see here is a zoom in. So if we take the previous plot and we take the region here near the present time and we zoom in, then this is what it looks like. So we are here at the beginning of 2026, and this is the current solar cycle that we are in. You can see that the maximum of the solar cycle has happened sometime in 2025, and now the solar activity is on the decreasing phase, but it's still fairly high compared to, for example, solar minimum, which happened in 2020. So this is a time when many solar eruption can take place, and where we expect space weather to be happening. Now, I wanted to say something also, in addition to the sunspot number and solar cycle. I wanted to say something about a very important graph that you can see here. It's called a solar butterfly diagram. So the butterfly diagram is something that we can make, and it's like the footprint of the fact that the sun is not constant, but changes all the time. And you can see that it's got this beautiful butterfly shape. So how is this diagram made? If you take an image of the sun with the sunspots on it, so for example, you can see here, these 3 sunspots have been identified for study A, B, C. What you can do is you can measure the latitude of the sunspot, And for example, for the sunspot A, the latitude is minus 15 degrees. And what happens is that if you repeat these observations for every day, and you make a plot of the latitude of the sunspot versus time, for each sunspot that you can see, you obtain this pattern. And this pattern tells us that at a certain point in the solar cycle, the sunspots are mostly at latitudes between around, say, minus 30 degrees and plus 30 degrees. So the sunspots at this time are only down here or up here. And then as time continues, the latitude of the sunspot decreases. So there is a migration of the sunspots closer and closer to the line here, which is the line of latitude equal to 0, which is the solar equator. So this tells us that the evolution of the magnetic field of the sun has an influence on where the sunspots appear. And interestingly, this butterfly diagram is a diagram that was discovered in the UK. It was made for the first time in 1904. And at that time, there were no computers. So the scientists who made this had to do this by hand. So you can see in this, if we zoom in one bit of this diagram, you can see that all these lines were traced by hand, and they indicate the latitude of the sunspot versus time. And the scientists that made this discovery are shown here. They are Annie Maunder and Walter Maunder. And it was an amazing discovery for them to find out that there is this pattern in the solar activity and where the sunspots are located. So now let me say something about what the sun is made of. So the sun is made mostly of hydrogen. The vast majority, 92%, is hydrogen. There is about 8% of helium. And then also there are many other heavier elements that make up the sun. And the sun is essentially a huge ball of gas. So it doesn't have a solid surface like the Earth. It's a huge ball of gas. And interestingly, it's in a state that we are not very familiar with. So what you can see here is a diagram of the different states of matter. You are very familiar with the solid state, the liquid state, the gas state. But when we are looking at space and astrophysics, actually many bodies are not in a normal gas state, but they are in a different state, which is called plasma. So in which way is a gas, say, for example, the air in the atmosphere of the Earth, different from a plasma? Well, we know that when we have a normal gas, the constituents of the gas are atoms or molecules, and these are overall electrically neutral. But when you look at a plasma, what you have is that the atoms are no longer together, and the nuclei of these atoms and the electrons have been separated from each other. And so you have lots of charges, positive charges and negative charges that are moving around. So for example, for the case of, and by the way, this kind of plasma state is obtained when the temperature, which is a measure of the energy of the body that you are looking at, is extremely high. Okay, so there is a lot of energy in the sun, and so most of the particles are in this plasma state. So I said earlier that the sun is made mostly of hydrogen, and so here you have a schematic on the left of a hydrogen gas. So we think of atoms in a hydrogen gas as neutral quantities, where you have a positively charged nucleus, which is just one proton in the case of hydrogen, and an electron that is orbiting this proton. Okay, so this is the gas state. On the right-hand side is the plasma state, where the electrons have kind of split away from their nucleus, the proton. And so the electrons are free to move independently as they want away from the protons, and the protons are also free to move as they want. Okay, so whenever we study astrophysics and we study space, in many cases, what we're looking at are plasmas, and we have to develop new theories compared to the study of neutral gas that we're so familiar with down here on the Earth. So now let me show you a movie that shows a solar eruption. So what you're looking at here is you're looking at the sun using an instrument called the coronagraph. And a coronagraph has got a disk in front of the instrument, this disk that you can see here. And the disk is occulting the disk of the sun, because the disk of the sun is extremely bright, and so we want to block it in the same way as it happens during solar eclipses. We want to block the light of the disk of the sun, and this reveals everything that is around the sun in the outer layers. And so what you can see in the movie is you can see that there is material that is continuously ejected out into space. Okay, these are called coronal mass ejections, and they are huge ejections of material into space. And if you look very carefully in the movie, what you can also see is you can see some dots on the image from time to time, not all the time, but sometimes following a coronal mass ejection, you can see dots. For example, now you can see some dots everywhere on the image. And these dots are actually energetic particles that have been accelerated during the solar eruption. So we know that solar eruption provide a lot of energy to some particles that are part of the sun, for example, protons, and then these protons can escape and travel through space. And they have a very, very high speed, sometimes close to the speed of light. So these particles are what we call SEPs, solar energetic particles. So here in this diagram, what you can see is the sun, you can see the earth, and there is a schematic of these energetic particles that have been produced during a solar eruption. So the SEPs consist of ions and electrons. The electrons are faster, and the ions arrive a bit later. And essentially, what is interesting is the fact that these particles are a radiation hazard. Okay, so you have all heard about radiation. Radiation is something that is not good for you. It's something that modifies the DNA in the cells of the human body, and therefore can produce actually health damage in a person. And so these particles from the sun are actually a radiation hazard. So now what you see here on the right side is a graph of the flux of solar energetic particles versus time. And so you can see that there is one part of the graph, this part here, where the flux of the particles is low and steady. And then all of a sudden you have this increase in the flux of particles and then a slow decay. So this is what we call a solar particle event, and the different lines correspond to different to protons of different speeds and different energies. Okay, so what happened is that somewhere around this point, so each of the ticks here on this plot corresponds to 1 day. So what you have is that sometime around the 360th day of 2001, which is in December, there was a solar eruption, and then suddenly part of the flux of particles increased and remained quite increased over some time. So what happens is that these particles are ejected into space, they travel through the whole of space, and they may reach the region near the Earth. So the Earth is here. You can see it in this schematic. And the Earth has a magnetic field itself. So earlier we talked about the solar magnetic field, but we know that the Earth also has a magnetic field. And the Earth's magnetic field creates like a region around the Earth, which is called the magnetosphere. And essentially, the magnetosphere is like a protective layer around the Earth that protects us from the bombardment from all sorts of particles and things that come from space. So what happens is that the energetic particles from the sun reach this region near the Earth, and if they are energetic enough, they might actually be able to travel across the magnetosphere and precipitate down at lower levels close to the Earth. And you can see that because the magnetic field lines of the Earth have got this shape here over the poles, so they kind of get together close to the poles, we expect that particles from the sun will be able to reach the poles easier then they reach, for example, regions here down near the equator. And this is exactly what happens. Quite interestingly, when these particles from the sun reach the atmosphere of the Earth and travel down the atmosphere of the Earth, what can happen is that they can collide with atoms in the atmosphere of the Earth and molecules in the atmosphere of the Earth. They can produce a nuclear reaction during this very high energy collision. And as a result of this collision, many other, we call them secondary particles, are produced. So you can see here, these N indicate neutrons. We also have pions and all sorts of other subatomic particles get produced. And then these secondary particles travel lower down into the atmosphere of the Earth. And this can be caused by SEPs, solar energetic particles, and it can also be caused by other very high energy particles, which are called cosmic rays. So we have a lot of energetic particles that come from our galaxy. They're called galactic cosmic rays. And so this is another type of very high energy particle that can reach the atmosphere. So we have this shower of secondary particles that get produced by this process. And sometimes the effects of these things can be felt even on the ground at the surface of the Earth. So what you can see here is a plot of what we call a ground level enhancement. So you are looking here at the increase in the number of neutrons that are detected at the surface of the Earth. Okay, so initially here we have 0 neutrons detected, but we know that on this particular date, which was the 11th of November 2025, there was a very big solar eruption, and lots of energetic particles were produced at the sun. And then, as a result of these particles hitting the Earth's magnetosphere, neutrons were produced, and this is why these detectors, so all the different lines correspond to different detectors, neutron monitors detectors. So these neutrons were detected and lasted for some time, as you can see here, several hours, producing a very strong enhancement in neutrons. So the different curves correspond, as I said, to different neutron monitors. And for example, this pink one here is a neutron monitor, which is located at the South Pole. It is at high altitude of almost 3,000 meters. And so this is why this particular neutron monitor detected a lot of neutrons. It is located very close to the pole, and it is at high altitude. But there were also other neutron monitors that detected the neutrons. For example, this green one here is in Finland. So they also detected neutrons as a result of the solar event. This is the curve for Calgary. And even in Mexico, which is not that far from the equator, they detected a few neutrons that you can see here. So why are we interested in these particles? We are interested in them because they are a radiation hazard, as I said earlier. So if you are an astronaut and you are in space doing, for example, a spacewalk, as you can see in these pictures, then solar energetic particles are a very big threat, because you can basically be subject to very high radiation dose if the sun goes off and produces a solar eruption right at the moment when you're out there unprotected, with the only protection of your spacesuit. In addition, if you have satellites in space, of which we have lots and lots, so these days we are very dependent on satellites, and there are many, many electronic instruments in space, so they are also subject to the effects of radiation, and the effects of radiation can damage instruments and electronics on board the satellites. So it has happened in the past that satellites have been knocked out by solar events. And the other thing that these particles can do is they can disrupt the communications over the poles, because over the poles they use a special type of communication which is called HF communication for airplanes, and essentially the communications can be disrupted. So these are all space weather effects of solar energetic particles. There is also something else that is very important and has been in the news recently, that I'm going to talk about in a minute, which is that aviation can also be disrupted by solar particles. So here in this schematic, you see all the different things that are affected by space weather. So there are astronauts, as I mentioned here, there is aviation, and then lots of other technologies in space can be affected by space weather. And the way in which aviation can be affected is as follows. So when you have one of these energetic particles arriving in the atmosphere and producing secondary particles, a single high energy particle produced, when it passes through an electronic circuit, can produce an additional current pulse. Okay, so this produces a glitch in the electronics. And these days in the airplanes that we have, there is a lot of electronics, and there is a computer on board that mediates all the actions taken by the pilots. All the commands of the pilots are passed through a computer, and then they get to the mechanical part of the airplane that is going to produce what the command intended. So, for example, turn the airplane on to the right, turn to the left, whatever. So if you have a particle that produces a spurious glitch into the electronics, this can give a kind of a fake command to the electronics of the plane and creates real issues. So you may have heard that recently Airbus has basically recalled 6,000 of their planes to update the software, because what they found out is that their software was prone to malfunction when one such event takes place. So what they said is that intense solar radiation may corrupt data critical to the functioning of the flight controls. So luckily these days it is possible to make the software resilient to these type of events, but in the initial version of the software, this was not the case. And so there was an instance where a particle hit an airplane in over Mexico, and this plane lost altitude very quickly, too quickly, injuring several passengers. Okay, so now let's say a few words about the kind of research that I have been doing. There are many questions connected to solar energetic particles that I've been working on, and the kind of things we would like to know are the following. So how do these particles propagate through space to reach the Earth? We know that they are produced at the sun, but then they have this huge region of space that they need to traverse. We want to find out how they propagate through it. Second, we want to be able, ideally, to forecast their arrival. So we know we are all very used to terrestrial weather forecasts when we look at the, at the forecast, and they're usually quite reliable and we make use of it. So we want to do the similar thing for space weather, being able to forecast, be careful, there's going to be a particle event coming up. And the other thing that we want to know is what is the largest possible radiation dose that somebody may get. Somebody like an astronaut, we need to be prepared and avoid really bad health effects for astronauts. So in this plot, you can see something that is not data. So this is not data, it's not a measurement that we have, but this is the output of a model. So we are trying to model the solar particles and make a map of where they're going to be located in space near the sun. So when we want to try and do that, what we need to do is we need to study the magnetic field that is present in space, in the space between the sun and the Earth. So you can see that in this plot here. So here we have the sun as this dot, we have the Earth here. And what we know is that there is a magnetic field in space in between, and the magnetic field is not straight, but has got this spiral shape that you can see here in the plot. Okay, the spiral shape comes because the sun is rotating. It has a rotation period of 27 days, and essentially it produces this pattern in the magnetic field line. So this here is a plot of the magnetic fields in over the distances of the order of 1 astronomical unit. So 1 astronomical unit is the distance between the Sun and the Earth. So this distance here, we call it 1 AU. When we zoom out and we look at the same magnetic fields over distances that are much larger, so distances of about 100 AU, then this is what the magnetic field looks like. It's got this winding pattern. Again, it's a spiral, but it winds on itself many times between the Sun and about 100 astronomical units. And you can see here that this is what we call the equatorial plane. And if you go at different latitudes, so higher up here, then the magnetic field is wrapping around the cone that you can see here, one at mid latitudes in orange and one at high latitudes in red. So there is a magnetic field. This is a big effect on charged particles. We said that the Sun is made of charged particles, mostly protons. And so when you have a charged particle, if it's propagating in a region without any magnetic field, so the lower half of this picture here does not have a magnetic field. So a particle not subject to a force is propagating in a straight line. On this upper half of the diagram, there is a magnetic field. The magnetic field is a vector that is pointing out of this plane, out of the screen, as indicated by these circles with a dot in the middle. And so when the charged particle that started here encounters the region where the magnetic field is present, then the trajectory of the charged particle starts curving. It produces this curved path, and it continues curving until it exits the region where the magnetic field is. And then here it continues in a straight line. So what this means is that when we have a magnetic field, the trajectories of the charged particles get curved around. And here you can see a spiral, which is a different kind of spiral from the one that I showed before. This one here is a kind of helix that is wrapped around the direction of the magnetic field. And this is how charged particles actually travel around in space. So in my work, I have been trying to study how particles propagate through the magnetic field of space and all the way from the Sun to the Earth. So here in these kind of plots, the Sun is at the center, here and here. And this is the projection from the top. So we are looking at a slice through the equatorial plane that I showed you earlier. And this is a projection when you look at the Sun from the side. And you can see all these different dots here are particles. The position of the particle has been calculated by using a model that describes their propagation. So I'm not going to talk a lot about maths and equations and so on, but just to say that we need maths in order to describe the position and the velocity of these particles over time. And so these are two equations that describe the evolution over time of these of the position and velocity. So what we do is we write the equations, then we solve the equations using a computer, using numerical programs, and then we produce the plots such as this one, where we have the position of the particles over time. And in the movie that you see here, this is an animation of where the particles that started at the Sun are going to be over time. So they're basically bouncing around through space and filling entire regions of space after having been accelerated at the Sun in solar eruptions. So just briefly, something else that we've been working on is the fact that I said earlier that the particle paths are helices, but when the magnetic field is not a constant, but is changing, is different in different parts of space, then what you have is that the helix is not actually a perfect helix wrapping around the magnetic field, but it's some kind of helix that is drifting around. So this is an important characteristic of charged particles trajectories in the space between the sun and the Earth. And in my research group, some of my students have been working on trying to understand this process of charged particle drift. So I just thought I would show you briefly some of the plots that come out of our simulations. So here you can see some plots that I have made using my test particle simulations, and you can see that what you're looking at here is you're looking at how many particles reached a given location in space. So if you imagine a sphere centered at the sun, and you imagine opening up this sphere and stretching it into a rectangle, then you get a plot like this, and each point in the plot, and in particular each color in the plot, tells you how many particles reach that particular part of space. So the bits where the red colors are regions where there was a very strong flux of particles, and then as you go from red to blue, the number of particles decreases. So you can see that when you do these kind of simulations, you can get a sort of map of which parts of space around the sun were reached by the energetic particles. And so, for example, in this particular case, there were some parts of space up here or down here where the particles didn't manage to get. Okay, the other thing we can do is we can study something called magnetic fluctuations. So some of you will have heard of turbulence when you are flying on a plane and you encounter a region of turbulence in the air. This makes the plane shake. Nothing to do with the aviation effects that I talked about earlier, by the way. But essentially, what happens is that the magnetic field also has turbulence. It has this kind of wiggly behavior everywhere. And so what you can do using our models is also to trace the paths of the energetic particles, which are these red paths shown here, in this complicated turbulent magnetic field. And what you can see is that when you include the turbulent magnetic field, the region of space where particles are located, shown by the colors here, is much broader than when you do not include it. So we are trying to have a description of the turbulence of the magnetic field and explain where the solar energetic particles are going to travel. We are also, in addition to doing the modeling in order to find out about the physics of these particles, we are also trying to develop forecasting systems. So we have been working with the UK Met Office to develop a solar energetic particle forecasting system. And we have, students at the moment and project students working with us doing this kind of work to understand the forecasting model and, of course, testing the forecasting with actual real data of solar energetic particles. And so what you can see here, you can see a cloud of particles generated by the forecasting system. And these are the profiles of particle flux and how it changes with time generated by the forecasting system. And so in conclusion, I hope I've convinced you that solar energetic particles are an important part to space weather because they are a radiation risk to astronauts, to satellites, and to aviation. And much progress has been made in recent years in understanding how they propagate from the sun to the Earth and in developing radiation storm forecasts. And I should say that there is a lot of things that we don't know about these particles. A lot more research is needed. So hopefully, if some of you are going to go on to study physics and do research in your careers, then maybe some of you can also be involved in all of this. And with that, I thank you very much for your attention.
Okay, thank you very much, Sylvia. That was really, really interesting. Lots to kind of consider. I'm sure people have got questions, so I'll just give people a minute or so. If you do have any questions, please pop them into the Q&A box in the chat function, and they should come through, hopefully, all being well, to myself. So someone has asked Sylvia, what is the most useful part of maths that's needed to research space weather?
Wow, very good question. So I think a very important thing is vectors. Yes, have you heard about vectors? Vectors is really important because, as I was saying earlier, we have these magnetic fields in space, and magnetic fields are vector quantities. They have a direction, and the direction is very important. So, for example, if you have a particle which is moving with a certain velocity, the inclination of this velocity with respect to the magnetic field influences the force that they experience. So you need to take into account the fact that both are vectors.
So I'm going to follow that up while we wait to see if anyone else has got any questions. But what is the most useful part of physics then that's needed for space weather research?
Okay, I think that everything connected with charged particles is very important. So electricity, magnetism are extremely important. And then you also need to know about gases. And yeah, these are the main things, really.
Okay, so another question. Would you say there's a link between dark energy and space weather?
Okay, well, at the moment, we are not aware of any process that requires dark energy to be explained as far as space weather is concerned. So this is where we are. We are not aware of any link or any need for dark energy. But we never know. You know, maybe some of you will find out that it's needed.
Okay, and Dave has asked, are there any careers within the telecommunication companies for solar physicists? And I guess that also extends out to kind of the aviation companies as well, right?
Yes, I think that there are, solar physicists definitely have career possibilities connected with the telecommunication systems, with the space industry. So you may have heard that there is a lot of activity connected with the space industry at the moment. And obviously, all I talked about today is connected with space and space weather. So space weather companies are very much interested in all these things. In fact, maybe I can show you a graph that I have. Yeah, this graph here is a graph that shows how many companies have been interested in subscribing to space weather alerts. Okay, so there is in the US, there is the Space Weather Prediction Center, and they give warnings about space weather. And this blue line shows you in time how many companies have been interested in getting information about space weather and warnings about space weather. So there is more and more interested in being prepared for space weather, and so there are also jobs connected with this.
So what kind of companies then are in that graph, Sylvia? Obviously, telecommunication companies, aviation companies, anything else that kind of takes a big share of that plot?
Yes, there's all sorts of things. I didn't talk about effects on electricity grids, but space weather also affects electricity grids.
Okay.
And it can affect the accuracy of GPS. So there are companies that use GPS for the most amazing things. So for example, shipping companies use GPS to dock their ships with very high precision. And during a space weather event, this precision can go down. So, there are all sorts of companies in this graph.
Interesting. Thank you. So Joe has also asked, do you use quantum physics in your research?
In my research, it's not necessary. So we do not need quantum physics to describe these particle propagation. But of course, it is needed to describe some aspect of solar physics connected with the nuclear reactions that happen in the sun. But most of what I talked about does not require quantum physics.
Thank you. And then we've got another one. There's no name on this one, but what does the butterfly plot mean or represent? So I think you showed that earlier in the talk.
Yes, so the butterfly plot basically tells you about a pattern where sunspots are not always emerging at the same latitude on the sun, but they emerge at different latitudes. And the reason for that is because the solar magnetic field evolves over time and it actually reverses. So what that means is that at a certain time in the solar magnetic cycle, as we call it, at a certain time in the solar magnetic cycle, the magnetic field points outwards in the north pole of the sun. And then over 11 years, then this direction of the magnetic field is going to become outwards, but from the south pole. So it's a bit like the pole is flipping from the north pole of the sun to the south pole of the sun. This takes 11 years. And there are mechanisms that happen in the core of the sun that make this happen. And so the butterfly diagram is the signature of these mechanisms that create the inversion of the solar magnetic field.
And we can track sunspots as well, can't we? Moving across different latitudes as that kind of process is taking place. Is that right?
Yes, we can track sunspots. We definitely want to track sunspots, and also for space weather. So whenever a new sunspot appears, it is given a number. They are all numbered and they are kind of checked because we want to know if they give off large flares, large solar eruptions. So there are catalogs of solar sunspots and all the activity that they produce.
Okay. And then we have another question. Who is your favorite physicist?
Oh, wow, this is too difficult. This is too difficult. But I have to say, connected to the talk, so I'm a fan of lots of different physicists, but connected to the talk that I gave, I'm a very big fan of Annie Maunder, I showed the picture when I was talking about the butterfly diagram. So she was a lady who worked at the Greenwich Observatory at the end of the 19th century. And she made some amazing discoveries about sunspots at a time when you may know that women were not really did not really have access to work, so most women were not working. And Annie Maunder managed to have a job as a scientist and make incredible discoveries.
Okay, thank you very much. Are there any final questions? I haven't got any more in my inbox here. I think we've had quite a few and some interesting ones related to what Sylvia's been talking about. So thank you very much, everybody. If there are no more questions, then we will finish. We are ever so slightly early, but that's absolutely fine. So my thanks to Sylvia again for giving today's talk. It's always really interesting to hear about how the research we do connects with our lives in the real world. And clearly it's got, lots of importance given how much we rely on kind of technology that can be impacted by space weather. So thank you very much. We will be running another online seminar probably towards the end of February after the half-term break. So if you have signed up for today's session, we will send out an email with the details at that point. Okay. So Happy New Year, everybody. Thank you for joining us, and we'll see you all again soon.
Bye, everybody.